The period of an oscillation is the time taken for one complete oscillation. Now, here I have the oscillating object. What is one complete oscillation? The equilibrium position, upper extreme, back to the equilibrium position, lower extreme, and back to the equilibrium position. This is one complete oscillation. The time taken for one complete oscillation is called the period of oscillation. And we generally represent the period by the uppercase T. Do not use the lowercase t for period. Period, the uppercase T of a simple harmonic motion, is the time taken for one complete oscillation. And what is frequency? Frequency is the number of oscillations per second. How many times the object moves up and down. Can you make a guess? How many times is this object moving up and down a second? Well, you can actually measure it. Well, this is about 3 times a second. It oscillates 3 times a second. Means the frequency is 3 per second. 3 oscillations per second. So frequency represented by the lowercase f is the number of oscillations per second, and it is measured in a unit called Hertz, Hz. What does Hertz stand for? It stands for per second, number per second. Alright. Period T and frequency f are related. Can you give me a relation between period and frequency? I just told you that the frequency of this oscillation is 3 Hertz. It oscillates 3 complete oscillations per second. Alright, if it does 3 oscillations per second, what is the time taken for one oscillation? Well, if it does 3 oscillations in 1 second, the time taken for one oscillation will be 1/3 of a second. If it does 5 oscillations in 1 second, the time taken for one oscillation will be 1/5 of a second. Is that right? Okay, now tell me, what is the relation between period and the frequency? One is the reciprocal of the other, or we will have f equal to 1 over t, or t equal to 1 over f. If the period is 2 seconds, if it takes 2 seconds for an object to complete one vibration, then it will only complete half a vibration in 1 second. You see that? If period is 2, the frequency is 1/2. If the frequency is 5, the period is 1/5. You see, one of them is the reciprocal of the other. Frequency is 1 over the period. Alright, let's now go back and get a couple of more important relations. Do you remember the angular frequency omega? What's the definition of angular frequency omega? Omega is theta over t. This is how we define it. Rate at which the angular displacement changes. So omega equal to theta over t. Now tell me, when this t is 1 period, what will be the value of this angle? When the time is 1 period. Now 1 period means, now what is the meaning of 1 period? This is the equilibrium position. Now, when it goes from the equilibrium to the upper extreme, the angle increases from 0 to pi by 2. Now, When it now comes back to the equilibrium position, the angle increases from pi by 2 to pi. And now it goes to the lower extreme, angle increases to 3 pi by 2. Comes back to the equilibrium position, the angle is 2 pi. So for one complete oscillation, the angle is 2 pi radians. That means when this time is 1 period, the angle corresponds to 2 pi radians. Therefore, if I replace this angle theta by 2 pi radians, this time will become 1 period. So, what is the value of theta for one complete oscillation? We already answered that. Theta equal to 2 pi for one complete oscillation. Therefore, when theta equal to 2 pi, the time taken for the angle to complete 2 pi radians is called 1 period. So when t equal to uppercase T, if this theta is 2 pi, then this time t will be the period t. Therefore, look at that very important, all-important relationship. Omega equal to 2 pi divided by the period. The angular frequency omega is 2 pi divided by the period. You cannot forget this relation. We will be using it as we go on several times. Alright? Angular frequency omega is 2 pi over the period. Alright. We can also write it as, look at this, 2 pi multiplied by 1 over t, and 1 over t is the frequency. So I can also write it as 2 pi times the frequency. You see, the reciprocal of the period is the frequency. You must know both these relations. Omega, the angular frequency, is 2 pi divided by the period, is the same as 2 pi times the frequency. Alright? Now tell me, what is the cause of acceleration of an oscillating object? I showed you this. What is the cause of acceleration? When the spring is pulled down, you can see the spring has now potential energy. The spring is now pulling the object back. Now, the force applied by the spring to get its original position back is called the restoring force. Have you ever experienced the restoring force of a spring? When you pull a spring, the spring pulls you back. You see, it is this restoring force of the spring that provides the acceleration. When the spring is pulled down, the spring wants to restore itself. So that restoring force pulls the object back, and it is that provides the acceleration. So what is the cause of acceleration of a simple harmonic motion? When the ball on the spring is pulled down, the spring applies a force upward to restore its position. You see that? And that force, when the displacement increases, the restoring force F also increases. Is that right? You pull the spring more, the spring will pull you back with a greater force. As the displacement increases, the restoring force also will increase. In the opposite direction, of course. If you pull the spring, the displacement increases downward, the restoring force will be upward. That will be in the opposite direction. When the displacement increases, the restoring force F also increases in the opposite direction. And this can be written as, mathematically, F equal to negative ky. Or we say the restoring force is directly proportional to the displacement, and its direction is opposite to the displacement. That's the negative sign. K is a constant, and we call it the spring constant. You have done this in Physics 1. We talked about Hooke's law. So F, the restoring force on a spring, equal to negative ky, where y is the displacement. Now, it is this restoring force that produces the acceleration. So, if this object has a mass m, and the restoring force F is pulling it upward, well, that F will be equal to ma, is that right? Where m is the mass of this object and a is the acceleration. So if m is the mass of the oscillating object, then F equal to ma. So I can replace this F now by ma, and what does the equation now become? The equation now becomes, this F can now be replaced by ma. We have ma equal to negative ky. Alright, can you solve the equation for A? Solving for A, you can have A equal to negative k over m times y. But at the moment, do you remember, I pulled down this step too rapidly. I wanted to ask you, but I hope you haven't read it yet. Do you remember about 15 minutes ago, we derived an equation for acceleration of a simple harmonic motion? Do you remember that equation? Acceleration of a simple harmonic motion. Alright, can you look back? I told you you must remember that equation. Acceleration of a simple harmonic motion is negative omega squared y. A equal to negative omega squared y. So this is the acceleration that we are talking about. So we can replace this A by negative omega squared y. What does the equation now become? M times negative omega squared y. Ma now becomes negative m omega squared y equal to negative ky. And you can see y will cancel from both sides, and you can solve for omega squared. Negative on the left and negative on the right will make it positive. Y and y will cancel. Divide both sides. Well, the simplest way is divide both sides by negative m, or negative my. I hope you have followed this. I don't have to do that. Divide by negative my, divide by negative my, and negative m will go, y and y will go, y and y on the right will go. We get omega squared equal to k over m. Beautiful equation. Alright, now tell me, give me an equation for omega that we have obtained a little while ago. Let's solve for omega from here. If omega squared equal to k over m, then omega equal to square root of k over m. Okay, now let me ask you, what is the equation for omega in terms of the period of a simple harmonic motion? I told you that is something you can never forget. But omega equal to 2 pi divided by the period. So let's replace this omega by 2 pi over t. We can now see 2 pi over the period equal to square root of k over m. Now, what are these things in here? This corresponds to the oscillations of a loaded spring. Well, what does T stands for? T is the period, the time for one oscillation. What does K stands for? K is the spring constant of the spring. What does M stands for? M is the mass of this object. So, we have 2 pi divided by the period equal to square root of k over m. Can you solve for t from here? What is t equal to? Well, I'm going to simply give it to you. I want you to solve it on your own. Solving for t gives me t equal to 2 pi times square root of m over k. Now, this is the equation for the period of oscillation of a loaded spring. That means the period of oscillation of a loaded spring like this is given by this equation, t equal to 2 pi square root of m over k. That means the period depends on the spring constant and the mass. Okay, and again, that is an important equation. T equal to 2 pi square root of m over k. Let's now talk about simple pendulum. A simple pendulum. Have you seen a simple pendulum? What is a simple pendulum? A simple pendulum is something like this. Can you see this here? A mass suspended by means of a string. If I pull the mass to one side and leave, you see what happens. The mass oscillates. And this oscillation is also simple harmonic. And this is called a simple pendulum. In fact, I don't know whether many of you remember, in the olden days, clocks used to run on a simple pendulum, oscillations of a pendulum. It was very widely used. The electronic age has actually taken away that beautiful pendulum clock. Well, anyway, the oscillation of a simple pendulum is a good example of a simple harmonic motion. A pendulum consists of a hanging mass from a string attached to a support at point O. There is the support and a string hanging from the point O, and the mass is attached to one end. A represents the equilibrium position. Now, this is the equilibrium position of the mass. The length of the string is L. When the bob, you see this mass is called the pendulum bob. When the pendulum bob is pulled to one position, what happens? When I pull it to the side and leave it, you see, when you raise it to one side, you give it potential energy. And because it has potential energy here, it's going to fall back to the equilibrium position. And when it comes back to the equilibrium position, it has acquired velocity. And that velocity will make it climb to the other extreme, like a swing. You see that? Just like the energy changes in the oscillating spring, here again we have energy changes. There, when the mass is pulled to one side, to position B, the string makes an angle theta. Now, just like the spring has a restoring force pulling the object mass, pulling the mass back to the equilibrium position, here again there is a restoring force, which is the component of the weight pulling it back to the equilibrium position. All right. If m is the mass of the bob, its weight mg acts vertically down. Is that right? If m is the mass of this bob, its weight mg will be acting vertically down. Now, this weight has two components. mg cos theta, well, this is the tension on the string. Now, the component of the weight mg cos theta in this direction balances the tension on the string. There you are. Now, this angle will be the same as that angle theta. So, this is the weight, the component of that weight in this direction will be mg cos theta. This is mg cos theta, which balances the tension on the string. And the component of the weight mg sine theta, look at this component, mg sine theta. What is the function of that? That is the restoring force. That is the force pulling the pendulum bob back to the equilibrium position. So mg sine theta provides the restoring force, pulling the mass back to position A. So when you, now watch here, when you pull the mass to one side, what happened? There is a force pulling this mass back to the equilibrium position there. That's why it comes back. So this mg sine theta is that restoring force. And this produces an acceleration. It makes the bob accelerate towards the equilibrium position, so that when it reaches the equilibrium position, it will have a maximum velocity. And this mg sine theta is the net force producing the acceleration on this mass, so that mg sine theta equal to negative ma. Now why is it negative? Because the acceleration is opposite to the displacement. Alright, now we can see m and m will cancel, and solving for a gives you a equal to negative g sine theta. This a is the acceleration produced on the pendulum bob by the restoring force. So a equal to negative g sine theta. Well, let's now get a reasonable approximation for this sine theta. The distance from A to B is the displacement of the mass. Is that right? The mass has been displaced from A to B, that distance. I'm going to call that distance x. When the amplitude of oscillation is small, this displacement is approximately equal to x, so that sine theta equal to x divided by L. You see, L is the length of this string. Sine theta equal to x over L. This is the sine theta. Sine theta is opposite side divided by the hypotenuse. So sine theta equal to x over L, which is an approximation. It works only when this angle theta is very small. If the angle theta is large, that approximation is a very poor approximation. Alright, now if you replace sine theta by x over L, can you now rewrite the equation for acceleration? The equation for acceleration now becomes negative g times x over L, where x is the displacement, L is the length of the pendulum. Alright, do you now recall the equation for acceleration we developed for simple harmonic motion? What is the acceleration for simple harmonic motion? Do you see I rewrote this equation as negative g over L times x, where what does x stand for? The displacement. Alright, but acceleration for a simple harmonic motion, I was asking you that question. Do you remember the equation we developed for acceleration of a simple harmonic motion? I know most of you forget all these things very easily. Acceleration A equal to negative omega squared y. There you are. A equal to negative omega squared y. We are now going to compare these two equations. Look at this. A equal to negative g over L times x. What does this x stand for? Displacement. This is for the simple pendulum. And this is a general equation for acceleration of any simple harmonic motion. A equal to negative omega squared y, where y is the displacement. So x and y are both the same. That means if you compare the two equations, this g over L for the simple pendulum stands for this omega squared. Don't you see it? Alright, comparing these two equations, we have omega squared equal to g over L. Now remember that x and y both stands for displacement. Therefore they are the same. Omega squared equal to g over L. Do you recall what omega is? Can you write omega in terms of the period? Yes. Omega is 2 pi divided by t. Omega squared is 4 pi squared divided by t squared. Alright? Can you solve for t from there? 4 pi squared over t squared equal to g over L. Can you solve for t squared from this equation? Well, t squared equal to 4 pi squared times L over g, and take the square root of that. T equal to 2 pi square root L over g, and this is the equation for the period of a simple pendulum. So I want you to now go back and tell me what is the period of oscillation of a loaded spring that we developed. Well, we developed an equation for the oscillation of a loaded spring. What is the equation for the period of oscillation of a loaded spring? Is T is 2 pi square root m over k. Alright, look at the period of oscillation of a simple pendulum. T equal to 2 pi square root L over G. They are similar, is that right? Alright, you must be familiar with these equations. Let's now talk about another type of pendulum called the physical pendulum. What is a physical pendulum? Now, look at a meter rule I have. If I drill a hole in the meter rule and suspend it, allow it to hang from that hole, this is the equilibrium position of the ruler. If I now pull the ruler to one side, look at this, and leave, the ruler will oscillate about the mean position. This is called a physical pendulum. Alright, let's talk about this. A meter ruler of mass m suspended from a rigid support at A, there you are, is a physical pendulum. Now this is where the ruler is suspended. It is free to oscillate at that point. And this is the center of the ruler, the center of gravity. You know that the center of gravity is the point at which the weight of an object is acting? Alright, the center of gravity of the ruler is G. And the distance of the point of suspension, well, let's go back and look at this again. This is the point of suspension. Let me find a hole in the ruler. And, well, this is my point A. And if the center of gravity is over here, the distance measured from the point of suspension to the center of gravity, we are going to call that by the uppercase D. So what does uppercase D stands for? The uppercase D stands for distance from the point of suspension to the center of gravity of the meter ruler. point A is at a distance d from the center of gravity of the ruler. If the ruler is now pulled to one side and released, it will oscillate in simple harmonic motion. At any given time, the ruler makes an angle theta with the original position. This is the original position. At any given time, the ruler can be somewhere here, making an angle theta with the original position or the vertical. Alright? Now, this is the distance d. This is the center of gravity of the ruler. Okay? At this position, the weight of the ruler mg acts vertically down. You see, the weight of the ruler will be acting at the center of gravity, will be vertically down. This is the distance d. The weight mg of the ruler is acting vertically down. Alright? This weight produces a torque. I hope you'll remember the concept of torque. You see, when the ruler is displaced, it has a weight mg. And what does that weight do? Weight wants to rotate this ruler. You see, rotation is produced by a torque. So this weight now produces a torque about this axis so that the ruler rotates. So the rotation of the ruler is produced by a torque. And I hope you understand, you remember this. Tau, the Greek letter tau, represents the torque. So the weight produces a torque tau about this pivot position such that tau equal to negative mgd sine theta. Do you understand this equation? Now, if you remember what we did in physics 1, torque of a force about an axis is the force multiplied by the distance. Look at the perpendicular distance. It is this distance. And if this angle is theta, this distance is d, this distance will be d sine theta. Let me draw that for you. Now, this distance is d sine theta. And now, the torque produced by this force about this point will be this force multiplied by that distance. You see, this distance, which is d sine theta, and this torque is a clockwise torque, which is negative. That's why we said tau equal to negative mg d sine theta, and that is the torque produced to make the ruler rotate back. Alright, but again, you have to recall a number of results we did in physics 1. Tau equal to I alpha. In the same way as in linear motion, F equal to ma. In rotation, tau equal to I alpha. So we're going to replace this tau by this I alpha. Here I is the moment of inertia of the ruler about the pivot point, and alpha is the angular acceleration. Is that right? I is the moment of inertia of the ruler about this axis, and alpha is the angular acceleration. Therefore, replacing this tau by I alpha, look at the equation we generated. I alpha equal to negative mg d sine theta. Alright, let's take this equation and talk about it further. Solving for that, let's solve for alpha from here. Alpha stands for the angular acceleration. You see, in the two previous cases, we solved for linear acceleration. But in this case, the acceleration is angular acceleration. Acceleration is negative mgd divided by I times sine theta. Well, I'm going to do a small approximation. When the angular displacement theta is very small, sine theta is actually the same as theta. Have you ever seen that? If the angle is very small, but remember, measured in radians. If the angle is very small, like 0.02 of a radian, sine of 0.02 radian is the same as 0.02. You see? Sine theta is approximately equal to theta when that theta is very small. So I'm going to replace this sine theta by theta, and what will be the angular acceleration equal to? Alpha alpha stands for what? Angular acceleration is negative mgd over I times theta, where theta is the angular displacement. Alpha is the angular acceleration, theta is the angular displacement. Now, this is the equation for this physical pendulum. Now, can we now compare this with the equation for the simple harmonic motion we developed earlier? Do you remember that equation? This is the third or fourth time I'm asking you, do you remember the equation for acceleration of a simple harmonic motion? I don't think many of you remembers. It is A equal to negative omega squared y. Look at this. Acceleration, displacement. Let's go back to this equation here. Acceleration, displacement. So this equation and this equation are the same. The oscillations of a physical pendulum is a simple harmonic oscillation. The acceleration is proportional to displacement and is directed opposite to it. Just the same as this. Now, can you compare these two equations? Yes. We can now say omega squared equal to mgd divided by I, where m is the mass of the ruler, g of course is acceleration due to gravity, a constant, d is the distance of the point of suspension from the center of gravity, and I is the moment of inertia of this ruler about an axis through the point of suspension. Alright, now you know omega. Omega is 2 pi over t, and omega squared is 4 pi squared over t squared equal to mgd over I. Let's solve for t from here. Solving for t, I get t equal to 2 pi square root I over mgd. And this is the equation for the oscillation of a physical pendulum. Alright, we have now three important equations we developed. The general equation for acceleration of a simple harmonic motion, the equation for the period of oscillation of a loaded spring, t equal to 2 pi square root of m over k, the period of oscillation of a simple pendulum, t equal to 2 pi square root of L over g, and now the period of oscillation of a physical pendulum, t equal to 2 pi square root of I over mgd. Alright, we will in the next lesson be using all these to solve problems. Let's now talk about energy of simple harmonic motion. You see, the simple harmonic motion is made possible by the changes in energy from potential to kinetic to potential and so on. So we must have a fair idea of how these energy changes take place. When a spring is compressed or stretched by a distance y, the work done is stored as potential energy of the spring. Is that right? When a spring is either stretched or compressed by a distance y, the work done is stored as potential energy. Do you remember the equation for potential energy of a stretched spring? We did that in Physics 1. U equal to 1/2 k y squared, where y is the displacement. You see? So, when a spring is compressed or stretched by a distance y, the work done is given by W equal to 1/2 k y squared. This is the equation we developed in Physics 1 using the method of calculus. Okay. K is the spring constant and y is the displacement. Okay. This work done is a measure of the potential energy U of the spring. So what is the potential energy of a stretched spring? The potential energy U of a stretched spring is U equal to 1/2 k y squared, where k is the spring constant and y is the amount of stretch or the amount of compression. If v is the velocity of the mass at that instant, then the mass will have a kinetic energy given by k equal to 1/2 mv squared. That means as the mass oscillates at any given instant, there is some potential energy in the spring given by 1/2 ky squared, and there is some kinetic energy of the mass given by 1/2 mv squared. So what is the total energy of the system at any given instant? The total energy is the sum of the potential energy and the kinetic energy. So I can write E, the total energy is U plus K, which is 1/2 ky squared plus 1/2 mv squared. Now we are going to take some specific positions and talk about this. All right, let's do that over here. At the two extreme positions, what is the velocity of the mass? You see, at the two extreme positions, the mass will be momentarily at rest. The velocity will be 0. That means at those two positions, the energy will be purely potential. There will be no kinetic energy. At this time, its displacement is maximum. Is that right? When the mass is at the upper extreme, the displacement is maximum. In other words, this y will be equal to A. What do you call the maximum displacement? There's a name for that. It's called the amplitude. So when the mass is at the upper extreme, its velocity will be 0 and its displacement y will be equal to A. Therefore, what will be the energy at that time? There, its kinetic energy will be 0. At the upper extreme, the kinetic energy is 0. The potential energy, look at this. This will be 0 because V is 0. The potential energy will be 1/2 K. In place of Y, I will use A because at that time, the value of Y will be the amplitude. Will be 1/2 K A squared. The potential energy U equal to 1/2 K A squared. I hope you can read that in the recording. And K, the kinetic energy, equal to 0 at the upper extreme. The total energy at this time, therefore, is 1/2 K A squared plus 0 because the velocity is 0. And so, the total energy at the upper extreme is 1/2 K A squared. How about the total energy at the lower extreme? Will also be 1/2 kA squared. Although the potential energy and kinetic energy keep changing, the sum of these two always remain a constant. The law of conservation of energy tells you that energy can change from one form to another, but the total energy remains a constant. So, if this is the total energy at any given time, this total energy must be equal to this total energy when it is at the upper extreme or at the lower extreme. Therefore, the total energy of oscillation at any given time can be represented by this, equal to 1/2 kA squared. Alright, so if I ask you, what is the energy of oscillation, or what is the energy of a simple harmonic oscillation, you must tell me immediately E equal to 1/2 kA squared. Alright. When does the oscillating object has the maximum velocity? We talked about it. The object has the maximum velocity at the equilibrium position. As it goes towards both extremes, the velocity decreases, becomes 0, and then increases to get the maximum velocity at the equilibrium position. So at the equilibrium position, all the potential energy is lost. What is the potential energy at the equilibrium position? There is no potential energy because the spring is not stretched or compressed. At the equilibrium position, there is no potential energy. All the energy is kinetic. So look at this. At the equilibrium, kinetic energy is 1/2 mv max squared. Look at the way I wrote velocity. The velocity at the equilibrium has the maximum value, so I wrote V sub max. Kinetic energy is 1/2 mv max squared. Potential energy is 0. So, now this is the case, the same case of the horizontal oscillation as well. Now, let's take the case of the horizontal oscillation and represent the energy changes graphically. Alright? An object of mass m is attached to a horizontal spring and is pulled to the right. That means x is the displacement there, and released. Alright? How do the potential energy U, kinetic energy K, and the total energy change as x changes? You see, when the mass is at the equilibrium position, x is 0. When x is 0, the potential energy is 0. The kinetic energy is maximum. When x is maximum, potential energy is maximum, kinetic energy is 0, and so on. Let's represent these graphically. Now look at this. This represents the variation of x. X equal to a cos omega t. Well, it means at t equal to 0, the object is at the right extreme. That's why we use the cosine function. This is a cosine graph. Okay, when x is maximum, look at the potential energy. Potential energy is maximum, kinetic energy is 0. There you are. Now, when x is 0, look at this here. When x is 0, potential energy is 0, kinetic energy is maximum. When x is at the other extreme, at the negative maximum, potential energy is maximum, kinetic energy is 0. Now, that means as x changes, potential energy changes, kinetic energy changes, but the total energy will always be the same. Look at this. This is a measure of the total energy, and that will always be the same. The energy keeps changing from potential to kinetic, but the total energy will always be the same. And what will be the measure of that total energy? It will be 1/2 Ka squared. Alright, look at this equation now. Kinetic energy changes, potential energy changes as the spring oscillates, but look at the total energy. Kinetic energy plus potential energy remains a constant. The kinetic energy changes, potential energy changes with time, but the total energy remains a constant. Alright, let's now obtain an equation for the maximum velocity of a simple harmonic motion. Where does the maximum velocity occur? The maximum velocity occurs at the equilibrium position. Since all the energy is kinetic at the equilibrium position, there is no potential energy. All the energy is kinetic. The velocity is the maximum there. Therefore, if V max is the maximum velocity at the equilibrium position, then the kinetic energy can be written as K equal to 1/2 mv max squared. The total energy at the equilibrium position, tell me, what is the potential energy there? Is 0. So the total energy is just the kinetic energy, 1/2 mv max squared. And you know that the total energy of a simple harmonic motion is 1/2 Ka squared. You see, that's equal to 1/2 Ka squared. You can now solve for Vmax. Can you do that? 1/2 and 1/2 will go. We can solve for Vmax. I'm going to leave it for you to solve that equation. You see, 1/2 mv max squared equal to 1/2 Ka squared. And therefore, Vmax equal to square root of K over m times A. Now, I don't think you will like me asking a question now. Some time ago, well, towards the beginning of this lesson, that was quite a while ago, over an hour ago, we obtained an equation for omega. Square root of K over m. Now, please go back and refer. It will be there. Square root of K over m is the same as omega. Alright, so replacing square root K over m by omega, we get V max, the maximum velocity is omega A. That's a very important equation. Alright, now I think we have spent a lot of time on the first part of this lesson. This lesson 1, this lesson I'm going to call lesson 1.1a. 1.1b will be using all the results we obtain here to solve problems. Alright, so I'm going to stop this lesson here. I want you to refer, go back and familiarize all the equations we developed. We're going to use that to solve problems. Well, I will see you for that part of the lesson a little while later. Okay.